My name is Homayoon Kazerooni. I'm a professor at the University of California, Berkeley, Mechanical Engineering Department. I've been here since '91. It's about 20 years, and I think I'm one of the luckiest guys, actually, to be able to the kind of work I did at Berkeley. I've been among a lot of good people, very talented people. I would say, without exaggeration, every single day of my life has been exciting. This stuff. It just, I can't take it anymore. It just, it really is that way. And so, what I want to tell you a little bit about the things we do with a lot of sharp students and engineers at Berkeley. That is also intertwined with my life now. 20 years. It was a job first. It was interesting, but now that I'm getting older, it's becoming a mission, becoming a lot more now. And we'll talk about it later on. But let's talk about engineering for a little bit. There's a concept called wearable systems. So robotic devices you actually wear, and it does two things. It gives you strength, and it gives you endurance. And these are really two different things that most of us are familiar with. When you go to gym, you actually do weightlifting, so that's really strength. And endurance is really no more than cardio, basically. Your oxygen consumption drops. You'll be able to actually go farther. You can walk farther. So is there any way we can have robotic devices? My very first failure. It's okay. It's okay. Is there any way that we can have robotic devices that, gives you strength and endurance? And it has many applications. And a lot of people ask me that questions. How did I get into that stuff? Is a long time ago when I was working on a lot of robotic devices, I realized robotic systems by themselves only can work on a very structured environment, like spray painting, assembly in cars, spot welding. You probably have seen a lot of videos of robots in other industry firms, and that's really good. But unstructured environment, like filling up the truck in a FedEx, right? Or working in a construction environment. These places you really can't replace a robot. You need a person. You need something very intelligent and adaptive to make decisions. And culturally, we can't replace people with robots. That's many places, that's really not an acceptable thing. And we need human in the loop at all times. And so we're accepting that on dangerous tasks, we do, replace people with robots. That's like, it's being done quite often. But we thought about coming up to a situation, why don't we combine intelligence of a person with the strength of the machine? So you bring them together, you create a better quality of work for these people, and that means large class of workers, warehouse workers, distribution centers, auto assembly, construction guys. This is sort of a dream for us. It's not going to happen very quickly, but if we trace everything we have now, it is coming up to maturity at some point. And then we also have a lot of people with mobility disorders that they don't even have the basic functions. And is there any way that we can have robotic devices that give them some strength to walk? They basically have to sometimes zero. If they're stroke patients, it's one side of the strength. So, so this really shows the history before I get to black and white photographs. This is like a color photograph. There are some histories you can go back, and I have lots of interesting photographs from General Electric when they thought, okay, we're going to make mechanical systems you can wear and you can jump over the building and bust through the doors. And it's very science fiction type things, which is really not real. And then until 1986, this movie Alien showed up. That was the very first time that they actually showed an application. And it took about 20 years or more that we came up with this device, which is really minimal. It really comes back to less is more. That you can actually carry heavy objects with it without risking back injuries in your back. The question really we were forming in about 20 years ago, how do I, for example, in workers, make them stronger in terms of moving around heavy objects, have a better work environment, and not to become injured in their back or their wrist or anything. So that was like our theme of the work. It wasn't about science fiction. It wasn't about jumping over the building. It wasn't about the stronger or something Superman at all. So that comes a little bit closer to what we were thinking about. And then in engineering, it's called exoskeleton because it's really outside of you. And the name it says it all. I don't have to explain that. And it really includes upper extremity and lower extremity, both of those. Upper extremity is for moving objects, and lower extremity is for walking. Very, very clear. But we have never really connected those together, mostly the way, because there is a technological barriers, and also there is no market needs. I'm the kind of person that I want to do. I really believe in less and more, because I believe in intelligence, but a smaller device that is accessible for larger, number of people. So we really never put this stuff together, and it seems to me that once you just make a whole device that you guys go in there and do everything, you just suddenly become Superman. And we haven't really done there because there is really a market need for it, so no one supports it anyway. It might look really good on TV and reporting, but there is really no application for our workers or patients here. And also we have some technological barriers to deal with that, which is not solved yet. Going back to the history, again, I apologize for the tone of this presentation. Most of our work is supported by Department of Defense, but it has application in all aspects of our life. And I'm hoping to show you that through these presentations here. So this is an application that Air Force were thinking about. It takes 5 men to load an aircraft, right? And in fact, actually, there is a 6. There is another one behind of this person that you can't see. In 1985, we came up to this concept of loading using this machine. Can we use this machine instead of forklifts? That has a factory application, as manufacturing application. We really never finished it, but that was really showed that that's possible. We had a device that rather than just lifting, you're actually able to manipulate, get a sense of how much you're picking up. Like if you're picking 200 pounds, you get a sensation of you're picking up 5 pounds. So you have that sense, which is a very good thing to have during manipulations. Later on, we moved on, and so again, going back to the less is more. We're trying to minimize and minimize, and I was all thinking about how to get this to people from the laboratory, which is always expensive and very complicated devices. But the real life requires something a lot simpler. So here you can see, this is again in the video, it's about 15 years old. You can see this robotic device. There is no really leg associated with that, and this person simply moves a big box of about 70 pounds, 80 pounds with 2 arms. Very simple. So that was a lot simpler because we don't need legs. And more importantly, we always believe that on a factory floors, if you are doing augmentation, if you're giving strength, there is really no reason to have legs. Everything can be hung from the ceiling. So why don't we just design an exoskeleton that comes down from the ceiling, and I can wear it and move around heavy objects, and just forget about the legs altogether. That would make the device simpler. So we did a lot of work, and this is a video of me on GM assembly, because I went actually to GM, and I saw a lot of these people. These are all my own photographs. I always wanted to know what they do and why do they get injured. They have back injuries all the time. And these guys do that once every 45 seconds. The car comes in and they pick up this, for example, this is a crankshaft. They pick it up and they go and put them in there. It's not that heavy, but they do it every 45 seconds or 1 minute throughout the day. And they go to a kind of, they call them repetitive injuries in their back. And by the time they get to the age of 45, their back is gone. So here you can see me the same thing, but now I have this glove, just a glove. So we got rid of the legs, we got rid of the torso, hands, everything. We just have a gloves, and the rest of the device is on a ceiling. In other words, we were trying to show this whole augmentation, the whole exoskeleton, the whole robotic devices you wear. It really doesn't have to be on you. It could be somewhere else. More importantly, what can it be if it is in a factory wall in the ceiling? Because real estate is pretty cheap on it, right? So you can just put anything you want on it. Right? So that was what my point here. That was a process of thinking against what media tells you, what everybody else says, what science fiction writers tell you. How many of you have seen Iron Man that you have to wear and jump around and save people? You know, that really is not the case. The question really is, can I save back of our workers? That's the question. You know, I'm not worried about wearing it or not. So eventually, believe it or not, we even did some more work for warehouses. Again, these guys, if you're familiar with these warehouses, these boxes come here, like from the factory, and these guys take these pallets, open, take the boxes, put them on the conveyor belt, and all these go somewhere else. They get distributed, and they all go like to a truck, and then from that truck goes to like another store or Target stores or Kmart or something. So these guys work all the time, moving a box very fast because the rate is pretty high. It's amazing how fast they work. In fact, they bring someone in the morning, an instructor, so they go through some exercise. They get warmed up before they do that. For a lot of us that work in front of a computer, these are very difficult jobs. Sometimes the warehouse is cold, sometimes it's hot, and trucks come in time, and they have to get filled up and go. And guess what? This is completely unstructured, and these workers do that. So we simulated that here in a lab. We don't have any conveyor belt, but you see the gentleman on the right side emulates a conveyor. And then the guy on the left is picking up 60 bucks poundage without feeling because there are two gloves. So the whole augmentation in exoskeleton manages two hands. Now this can be affordable and can be used by, and this is the other way around. You take it from the pallets and put them in a conveyor belt. So two lessons from this is, again, less is more is good for us. Number two is we don't really have to use, to copy biological systems. We have to do whatever we can to solve our problems. I remember a lot of my colleagues working on a grasping. Grasping by robotics is a very difficult job. How do I grasp on a box with fingers, mechanical fingers? That was really difficult. I bypassed all of that by making a plate and put pins in there that could come out by about 1 millimeter, and they go inside the box, and they penetrate, but 1 millimeter is not bad. And once we do that stuff, the technology goes out there, and many people can get benefited. It was a trade-off between compromising on scientific facts versus what people need. Again, this is a very interesting emulation. The gentleman on the right-hand side, on the left side, is a football player. And the one on the right side is a very small woman who's like probably half the weight and the strength of him. But they do the same palletizing rate, 14 boxes a minute, if you count this. And I want you to try that. Try to move something 10 times a minute, and that is an exercise, major exercise. And these guys do it, workers do it, 8 a.m., sometimes a lot earlier until 4 p.m. all the time. So this, we even did some stuff for United States Postal Service, the same technology. Now these are, it's started to get adopted now. We don't know yet, but it's coming up to a lot of manufacturing facilities. It's really, if you trace, it goes back to, yes, exoskeleton augmentation, but we strip down everything. We're left with wrist, just the wrist. And the price, almost $10,000, which is pretty good considering it minimizes the risk of injuries. It sort of shows the trend of work in engineering and being responsible as a scientist, what we actually create and what the result of our work will do. And especially among the students, we train them to be responsive to people, to industry needs. Currently, I'm working on a patient handling device. And these figures actually tell you the story pretty well. We're trying to move the patient from bed to wheelchair, wheelchair, bed, without jeopardizing the back of the nurses. Nurses go through a lot of back injuries if you read the literature. We're not there yet, but we're trying to do as much as we can with the intelligence of the computer. There's a lot going on here in terms of intelligence. The patient gets lifted. The person will feel probably about a few pounds for every 50 pounds. So if you pick up a 100-pound patient, you're feeling about 10 pounds. And then as it's heavier, then you feel more. And you can, of course, adjust that through the computer. We're not anywhere close to that because here you're dealing with two people. It's not a person and a box anymore. It's two people. And more importantly, she's vulnerable. You have to make sure that a lot of issues are taken care of before we actually lift the patient here. So we don't have anything there yet. In year about 2000, I offered the proposal to the Department of Defense about these workers that they carry major objects. You see that they carry up to 130 pounds, right? And biomechanics tells you that don't put anything on your back more than 30% of your weight. But these guys, they load them with sometimes, usually 95 pounds, but on missions that they have limited supply, 130 pounds. So that's, and the study shows 30%, 35% of them experience some sort of injury, right? So this is another case. Now, you see, you carry heavy objects, but the moment you carry heavy objects for a long distance, you don't use your hands anymore. It goes your back. So if I want to pick something heavy from here to that point, then I use my wrist and arms and hand. Whatever I have on that previous device will take care of it. But for long distances, you guys know, you just put it in the backpack, and these guys carry all kind of batteries, of course, ammunition, bedding, food, supplies, everything they have in there, and it gets to 130 pounds. And we came up to this concept. This is actually, I still have this napkin every now and then. I show this to my wife to impress her, but it doesn't work often. But so what it is, it's very simple. It's a backpack. We have a backpack with two legs and a computer. If you need the legs will come down and the backpack will walk behind you. And if you don't need it, take the legs out and you're left with your original backpack. Well, this to me was a concept of exoskeleton, which you can really use it to bust the doors or become science fiction type, George Lucas type robots. That's really different. But nevertheless, you're wearing it, right? And more importantly, you don't really need anything on your arms. So I don't need any gloves anymore. I don't need any hands anymore, right? I don't need two arms and two legs like Iron Man. And why would I need to carry things with my hand if I'm going long distances? In fact, I want to carry nothing. In fact, if you talk to soldiers, they don't drop their weapon. They always carry their weapon. There's nothing to carry, right? So we call that lower extremity exoskeleton. At the time, we called it lead. And it does strengthen endurance again. And really, it consists of two legs, power unit, and a backpack, and a computer, period. That's again, the minimalist approach. That means the least amount of things, but a great number of intelligence, a great deal of intelligence to make the machine accessible. To me, a word of accessible means a lot, because I see around and I see a lot of technology we have, but never gets to people because it's just not done properly. It's done, we have a tendency of adding things. I want to take things out to become accessible, but it still have the performance we're looking for. And that's really difficult. It has been very challenging, and sometimes against scientific approach about anything. Or why don't you put another arm in there, or sensors and computers, add and add, make it better and bigger and bigger. Yeah, make it bigger and bigger in the lab, but no one will use it. It never goes out. It's really a problem that I feel among a lot of engineering and scientific community, not only in US and Europe, but also in Eastern Europe, Asian countries. So the whole concept of lower extremity exoskeleton, again, considering a minimalist approach, was intelligence of a person, but a walking backpack. And I purposely did this cartoon to show you things are simple. You know, you don't have to make it really complicated, and it will work like that, right? And then you walk with it. And if you don't need it, take the leg off, right? And then we made it a little bit better, right? And then the Department of Defense funded it. We spent years here on this project, and that was our very first project that is posed for our funding agency. And of course, these are all the machines we built to just solve that problem. The 2 different versions came out. Let me show you this video here. You might enjoy this. I think rather than me talking, it's better that
by Berkeley Bionics. The system, completed at the beginning of 2005, has given birth to 2 subsequent generations that have military applications and promise to replace wheelchairs for many patients suffering from mobility disorders. The Berkeley Bionics Exoskeleton is a human augmentation robotic system comprised of 2 powered anthropomorphic legs, a power unit, a small onboard microcomputer, and a backpack-like frame on which a variety of heavy loads can be mounted. The Exohiker provides a user with the ability to carry loads up to 200 pounds with minimal effort over any type of terrain and for extended periods of time. With the exoskeleton, the user does not feel the weight of the load that is being carried. Therefore, this system increases the user's physical effectiveness significantly. There is no push button or keyboard to drive the exoskeleton. The user becomes an integral part of the exoskeleton while walking. An onboard microcomputer ensures that the exoskeleton moves in concert with the pilot, with minimal force between the exoskeleton and the user. A more recent generation has now been shown to reduce the energy required for a person to walk. Furthermore, the system reduces shock forces on the user's body when carrying heavy loads on descending slopes and stairs, particularly reducing stress in the knees and back. The exoskeleton virtually eliminates all load forces to the user's body, so the user can walk or even run comfortably while carrying heavy loads. The exoskeleton is comfortable and not confining. It effortlessly shadows the user and allows for a complex array of maneuvers, including those necessary in critical missions. The exoskeleton is ergonomic, highly maneuverable, durable, and lightweight. It can be taken off within seconds and with little effort. It weighs only 31 pounds, even when equipped with enough batteries for long-duration missions, and can be hand-carried. The exoskeleton can fit in a small box ready for shipment and deployment. The exoskeleton is designed with comfort features and ergonomics in mind. It can be put on in a few seconds without any assistance from others. An onboard computer instantaneously takes over control of the exoskeleton. Subsequent generations include a novel controller which has been shown to lower the user heart rate and oxygen consumption while walking. In situations where the backpack is not needed, or in emergency situations where high degrees of maneuverability and agility are required, the backpack can be instantaneously ejected without any adjustments to the exoskeleton. Furthermore, in situations where the exoskeleton is no longer needed, the entire exoskeleton can easily be taken off. Moreover, the exoskeleton legs can be stowed and carried like a backpack when they are not needed. This feature allows the user to perform demanding maneuvers while carrying the exoskeleton for later use. Robustness is a critical design feature in the exoskeleton. It can suffer through harsh environments and endure heavy abuse while maintaining functionality.
Sorry, this will take some time, but you can see that on my laboratory site at the university. But it tells you that it had a lot of intelligence within the computer to deal with all these features, and it was not even close to what Iron Man tells you or science fiction type should be. All it does allows that person carries a heavy object. That's really bottom line. I know it's not glamorous, but it was solving a serious problem that I'm aware of. And the third generation called HULK, Human Universal Load Carrier, and does have one more characteristic, and that means it minimizes the oxygen consumption and heart rate by about 10%, which is substantial, that you get less tired. A lot of applications in various industry for it. We did a lot of evaluation. Here's an evaluation in Colorado Rockies. You can see how steep it is here. And these are the power source here, the computers in the back, the legs down here, and weights are behind this gentleman. We did more evaluation on snow also. And eventually it was licensed to Lockheed Martin. So we no longer do. In fact, this is the same device built like a few doors in Echeverry Hall. Since then that I did my contract, the grant with the Department of Defense, then we moved on. I'm going to skip a bunch of engineering concepts here. I apologize how it works. But in case you're an engineer, you can talk later about it. If this is another thing it will show here. You can see you can wear the device here, and spine compression forces actually, when you wear the Ekso, actually drops by 50%. That was what I'm looking for, and you don't see it in science fiction devices. We moved on to using these devices with people with mobility disorder, and in particular, I was focusing on two classes of patients. One was the stroke patients, and one people who were bound to wheelchairs. And the reason I was focusing on these two, because again, these are high number of people go through stroke patients, and I can tell you a little bit more about it. And a lot of people are limited to wheelchair for mobility. That goes without saying. You just have to read the literature a little bit about what the consequence of using a wheelchair is. The moment patients sit on wheelchairs, the onset of a secondary disease will start because they have been sitting all the time. So you want to make sure these patients are upright and mobile. I shouldn't use the word patient, but you want them to be upright and mobile and walk around and do their daily tasks, right? And sitting at all times. So again, I was targeting the large populations, the one that is effective, the one that changes our lives. This is what our focus was. We started in about 5 years ago. Again, the stroke patients are one-sided. We get only in the U.S. we get about 800,000 stroke patients. About 150,000 will not survive. So we are left about 600,000 average just in the U.S. And top 8 European countries are also the same as U.S. So it's a really large quantity, a large number of people who, half of them, they no longer are able to walk properly, and you want to get them walking before they get onto the wheelchair. And then the second focus of mine was spinal cord injury. These are the guys who go through car accidents, mostly motorcycle accidents, car accidents, diving, all this, ski accident, unfortunately. And a lot of them are very young. And they go through a spinal cord injury, and they just basically, if they're paraplegic, they just have no functionality on their legs, and there's really nothing for them right now except wheelchairs. For stroke patients, what's the solution? They teach them how to walk this way. You put in a treadmill, and a physical therapist sits on one side, usually two, one on this side, one on the other side. Basically, they go through the trajectory of the foot. Hopefully, the patient will learn how to walk. And you have to go to a rehab center. The spouse have to take them there, right? Their friends have to do that, and it's labor intensive. It's patient's dignity is also something you have to pay attention to. So why can't we just give them a device that they take him home and practice at home in the privacy of their houses? That was my sort of solution for that. Getting a patient all the way from the home, put them in a taxi, go to a rehab center for 45 minutes, it's just not sufficient. And on the wheelchair side, which I call a mobility aid, provides independence, keeps patient upright and mobile, minimizes secondary injury, and it gives them involvement in daily activities. Once you're standing up, the doors will open. The only commercially available device for a stroke patient is actually this one, which is about 250,000, and you walk in there. So that's really what we have from Europe, actually. And again, you still have to go to rehab center. Again, going back to my approach of being minimal and bring the solution to people, that's just not acceptable. And it won't last long, probably a few more years. But what about if we give patients similar exo we gave to soldiers, and then we give them crutches and so to stabilize themselves, and they do that in the privacy of their homes, in their houses. So that's, well, in order to do that, we need a lot of engineering work, a lot of cleverness, a lot of inventions, a lot of being real, and ability to be flexible, an ability to drop things but maintain performance. That's a really amazing compromise that if we actually simplify our lives, simplify technology, and it simplifies our lives and creates a better quality of life for these guys. So it was a huge work for us from this, because that's easy. You put a gate and it's a stationary. You buy treadmill, right? You do all that stuff. Of course you want the $50,000. Right? But if I give them this, then they can walk around the hallway, in the garden, in a park, maybe a few hours a day rather than an hour every week. Right? So from here, so there are two other, so we're working on this in Berkeley, and there are two other entities working on this project. I have been in communication with both of them. They're good friends of mine. One is a technology called HAL from Japan, and there's another one called Rewalk from Israel. They use different technologies. HAL uses EMG signal to drive the machine. They got two arms and legs. It really is not useful for paraplegics because they don't even have any EMG signal like their legs, let alone. So, but nevertheless, it's in the right direction. And another one, Rewalk, from Argo Medical Technologies, which is now in US being evaluated, and then very good technology, both of them. And I'm glad to see others thinking the same way, bringing technologies to people who need it. So the first thing we did, it might sound really funny here, but we just took the same device that military guys wearing. That's the same device, actually. We started modifying a few things. We locked a bunch of degrees of freedom. We changed the software completely. Sensors changed, actuation changed, and we put them all together differently. And then we went to UCSF. I had a good colleague of mine, Dr. Nancy Beale, who is a physical therapist there. And we did some tests. And here's in a stroke patient. Whatever you see here in the back, these are all supports so he won't fall. It's our very first experiment we did. And you can see, this really shows how the bad leg follows the good leg. That means you're a stroke patient, one side is not good. So I don't want to go through details of that, but that simple experiment, the reason I'm showing here, that to me was, okay, I see some lights at the end of the tunnel that get information from the good leg, put them back on the bad leg so they would walk symmetrically and get trained. And that was our starting point. And you can see actually here that, like on patient one, no, actually, on this one is a good one. You can see I'm sorry, I think the rehab leg was red on the patient one, and then the green one was a healthy one, and then you can see the blue one is a rehab leg, just became just like the green one. But we were not completely successful in all the cases. Nevertheless, it was just giving us a level of hope, and you come the next day, okay, well, I didn't do well, but maybe later. So we did more experiments. We learned a lot. And then I think I'm going to go a little bit fast here. We moved on to using paraplegics in our experiments. So we worked with Dr. Mark Abel of the University of Virginia. And we tried various people who were either complete paraplegics or incomplete. And this is our really second experiment of our device over there. And this is a patient who hasn't walked for a while, but the machine is able to walk him. And what you see here, pretty soon they'll let go of a patient. I'm sorry? Oh, sorry, you can't see this thing. Okay, well, I'll have another one coming up soon. I'm sorry. So we did some experiments with this. You get a video in a second. The point is, we did a preliminary experiment with least equipment we had and least amount of funding we had. And we decided to go ahead for our final design. And it's very simple. That same Exo, you're wearing it. But now you have instrumented crutches, so the crutches tell you where the legs should be. So you put the right clutch out there, and then you provide a polygon of stability, and then the other leg will go next to it so you won't fall. And the whole idea was to have a device that allows these folks to be upright and mobile. And in 2007, we were able to get a contract or a grant from NIST. I was really happy when I got it because someone actually heard us. And within 3 years, we built this machine.
A person becomes paralyzed, a level of their independence is also robbed from them. And that affects us psychologically and our spirits. There's a part of us that dies. I've been trying to visualize myself a contraption that would enable me to get up and walk. I thought, well, is it going to be an avatar, perhaps a robot? And then I received the phone call to try this new technology, the e-legs.
I've heard from so many people that the first thing that they encounter after an injury or an amputation is the word no. And I think we are demonstrating here that there is no such word as no. Pheonix is really built on the platform or the legacy of Hulk. Hulk is an application that we made for the military, and we have licensed it to Lockheed Martin.
In 2005, when Berkeley Bionics was founded, we entered a license agreement with the University of California to commercialize the innovative exoskeleton technology that was developed at the Robotics and Human Engineering Laboratory. Pheonix is, as an engineer, one of the most satisfying projects to work on because it's an integration of so many interesting talents: mechanical engineering, electrical engineering, programming, control. And really, when you bring all of those aspects together, that's when you get a really innovative product.
To take my first step in the e-legs was just astounding because I bent my knee for the first time in 18 years. And I placed my heel on the ground, and then I transferred my weight, and then I took another step and another one, and it was so natural, and that was what really gripped me.
In my field, spinal cord injury, we work with people who typically are paralyzed for the rest of their life. For the first time in history, we can start to think about giving movement back.
So let me move on a little bit. I have just a few more minutes. So there are some difficult facts. People with mobility disorder generally have lower level of education. Unfortunately, they tend to be a little poor. They have They have disadvantages. Politically, they are not as strong as insurance companies. And there's really no solid research strategy to come up with this. No one can tell me this cannot be less than $10,000. No one cannot tell me the technology we have for a power wheelchair or a motorcycle is more than that. I cannot see it. It is possible to bring this to a large number of people with less than 10,000. So, after we did ELEGS, which is this one, it came out October 10, we decided to come up to something a lot less expensive. So my challenge was to my students is we want to make something less than $15,000, and we wanted to do it at the university with the help of the students, right? I mean, that's it. So that's, I don't know how simpler can I get. So then we came up to Austin project, which you might have seen that. Austin was an undergraduate who graduated last year, last May, 2 months ago. We worked with him for a long time, but we call this project Austin because we don't really have any other name for it. But it's truly low cost. It can be. But university is not in a business of selling devices. We develop technology and we show it's feasible. So we make this machine. It's very sophisticated in terms of software intelligence, but hardware-wise, it's really not much in there. And it also proves that's a direction we can go for providing these devices for thousands of people who might need that. I'm just giving you a few minutes of this video, if you don't mind.
Forever though on August 21st, 2007, when after a post-graduation party, being out and drinking, then I'm about a quarter mile away from my own house when I go too fast around a curve, and my rear tire hits the curb and spins across the road, and we wrapped on a tree at about 60 miles an hour. I guess I can't feel my feet. I don't really know. I probably can feel my toes, maybe not very much, but just below. And it's that little hope that I guess you hold on to. And no one wants to break that for you. And eventually, you're just going to have to put it all together and go, this is how it's going to be for life. You know, you spend so much time thinking, oh, what if? You know, what I would do to change it. And one day, this last summer, I got a email from a former UC Berkeley student. He told me, hey, why don't you get in touch with this professor? He's doing some really interesting research that you can be interested in. So I go over to his lab. The lab, I mean, it's a crazy place when the first time you ever walk into it. There are all these mechanical exoskeletons everywhere. It feels like you're just walking into a set of a sci-fi film. And basically, he tells me that he has a dream, that he wants to see me walk again.
Is there any way to create machines for people with mobility disorder to become involved, to do their job, and take care of their families, to enjoy the life as much as they did when they were mobile?
And this is the one thing that I and pretty much any person with paraplegia would do anything for. But yet, the one thing that pretty much no one can help you.
I don't have the ability to fix the spinal cord, but I do have a pretty good ability to make machines, and make machines that are really good at what they do.
The target, what you're looking for in Austin projects, is to create accessible exoskeleton systems for everyday use. Something very simple, something high performance, but with very low cost.
And then we basically start on the ground and then go from there. I'm passionate about it. Like I want to find a solution, and I think there's a solution out there. And then I basically just like think about the problem everywhere I go. And then if you think about it for long enough, eventually you come up with a solution.
Yes, I've been developing the code for this robot for a bit over a year now. So it needs to be very reliable, 100% of the time. Failure is never acceptable.
And that's what makes our project so sexy, is it's alive, it's real. And my job is basically to help them transform this computer model and help show what's going to really happen to it in real life.
This exoskeleton might seem rather revolutionary to that system, but I don't see it. I see a natural progression from the same glasses and hearing aid and prosthetic glasses to something a little bigger, maybe.
You know what I think we should do? I think we should try. I'd really like to walk across the stage at graduation.
You know, it's a massive milestone we've set for ourselves.
And I bet you no one has ever graduated with an exoskeleton on before.
So the suit needs to be functioning flawlessly at that point. And we're a long way from that day here.
Whoa! Well, do one track.
Let's have them all.
Okay.
Grab the chair.
Yeah, no, I got it. I'm ready. We're standing by us.
That's not what I'm used to.
Yeah, all right. Well, we had lots of load on your furnace.
Well, now just you guys working, I'd be great.
Yeah.
A lot of what is constantly being done here is problem solving. You know, we don't have a third knee because, you know, initially something was designed and then you have to make it better and better and better.
Good, our Hail Mary knee design here.
I don't think you can expect it to be perfect after the first shot, especially in what we're doing, because not a lot of people have done this before.
The point is I gotta get ahead here somehow. Because we're breaking stuff faster than we are testing.
Let's see, today is Tuesday, so we have Wednesday, Thursday, Friday, Saturday,
The hope is with this exoskeleton is that it can help negate those negative health effects that's brought on by sitting in a wheelchair. Beyond just the health side of it, though, there's also the mental thing. Like I said, being in a wheelchair. I can't tell you. I mean, at first, it's the big thing she misses. But as time goes on, it's not those things that you truly miss. It's the little things like being able to hug your mom, stand by your mom. You know, walking across the stage to accept a diploma. I've done lots of walking, you know, with the machine, but I can't imagine a moment still. I can't imagine what emotion it's going to bring out in me. It's going to be one of probably the most defining moments of my life. And having the opportunity, knowing that there is a possibility for these to happen again, that truly is beyond a price. That's truly magical.
Sheila from Ray.
It truly makes one rethink about what is possible, because that's surely what I would have said was that that's impossible. And I think that that's where we are today. It really makes me much more reluctant to ever use that word again.
Pretty much, I'm going to wrap up my lecture today. I have a lot more to cover in case you're interested later on. You know, we're moving on. This is really not my work. It's a work of a lot of people, a lot of students, a lot of, I would say number one thing is passion. Number two is using our knowledge for the passion. And number three is to recognize our fellow citizens' problems and using technology to solve this. There is really nothing in front of us to prevent us to get this to machine to many people except funding. This is not a session for fundraising, but just wanted you to know we are very lucky to be among a lot of talented students, talented people. I told you before, I've been very lucky to be able to do this stuff with people, and I want to make sure I put them in a good use. Being at Berkeley, this is only a very small project to me in comparison to many things we can do. You know, we have built all kinds of devices, prosthetic devices too. I'm not going through that, but we're very committed to do that, and that's the way Berkeley is. Thank you.
Thanks, Professor Kazerooni, for probably the first Science at Cal lecture that's brought a tear to the eye of many of us in the audience. I'm sure he'd be happy to take a few questions. Please, yes.
Your second generation device that you made for the military, that you said that it can lower the heart rate, and also what mechanism is that?
Oh, very good questions. The way it works is it emulates a situation that you're going downhill. So it looks like you're not working against gravity. If I work on a flat ground and I have a certain oxygen consumption and heart rate, if I go uphill, that will be getting more. If I go downhill, it gets lower. So it looks like someone is actually pushing me. So, but I can't increase that to 100% obviously. But you're able to drop it by about 10%. So you will be less tired. If I use the metric of oxygen consumption and heart rate, you'll be less tired, but the machine is actually pushing. It's a very strange feeling. Please.
Are these devices you're making right now, these prototypes, are they using mostly metals for the load-bearing components, or are you having high-strength plastics?
Mostly metal right now, but if they are for load-bearing devices, they're definitely metal. But for people with mobility disorders, usually not much load in there because they're on the ground. So we're hoping to use that eventually, some other composites. But right now, we're using whatever we have around, which is metal, aluminum, some parts are steel. But that really manifests in the manufacturing side of it. If you ever come to larger scale manufacturing and some other setting, then we have to be very precise about what materials we're using to, again, the cost comes down, becomes lighter, and has durability of some years. But we have other parts, plastics. The harness is obviously fabric and plastic and foam. Straps are all plastic. but the load-bearing parts are all metal.
It looked as though you had the first generation and the second generation device, and I think I saw mention that the second generation device actually had power input to it.
Yeah.
Does that imply the first one didn't? It wasn't powered, or
yeah.
Kind of confused.
The first generation device? No. Locomotion doesn't require power much because you're orthogonal to the gravity. So I just need to lock my leg and swing it, and lock my leg and swing it while the load always goes to the ground. So the first generation only had power for the computer to adjust those impedances. So it didn't have locomotion power. Right? That's what it would go for a long time. But guess what? With my age, I can't put 100 pounds on my back and stand. But with an unpowered machine, I'm able to hold this for hours. However, I can climb the stairs with it. I can come down the stairs with it easily. So the second generation had power and a knee, which allows you to climb. Very good question, by the way. I can't believe you caught that. That was good. And then the third generation had actuation at the hip. And again, going back to our approach being minimal, I mean, that's the reason we went all the way to Lockheed Martin took it, because it's real. If you look at all the other exoskeletons, they have powers everywhere. Yeah, $500,000 machine. What am I going to do with it? But you're right, the first one did not. In fact, you can use a backpack with a solar power and you can drive it for hours and hours because you only power a computer and a sensor and a bunch of valves, hydraulic valves, open and close. But inherently, no locomotion power was needed to get me go through a straight line. But my oxygen consumption would increase. Yeah, because it looks like, I can take an example later, but my oxygen consumption was high. But I wasn't feeling it. I was getting tired. But I wouldn't get any load on my knees. I can't even have 100 pounds on my back more than 10 minutes before I injure myself. But here I didn't even feel the load, but I could go. That was good. Thank you. I can talk to you. Please.
I'm curious what kind of sensors you have with the unit, whether there's sensors for accelerometers and
very good questions. Yeah, there are ground reaction forces measurements. So they measure from hill strike all the way to toe off. That's what we have. And that's the only information signal you get from the person and the ground, from the environment. Then you have another set of sensors on an actuation, which is accelerometer, position, and velocity. But our intention now in these new devices accessible to take them off and somehow to estimate, because that drops the cost and also makes it robust, last longer. If I don't have a sensor there, I don't have to worry about it. So it's all questionable, would that really drop the cost or not, right? I mean, I do anything I can, but I can't predict the future, but I just know they're expensive right now. A wheelchair, powered wheelchair is about $5,000 to $10,000, you want to get there. Of course, there's a lot of manufacturing tricks you can make it lower cost, but you're right. There are all kinds of sensors, but the approach is not to add. Try to have minimal number of. Basically, you want to rely on less hardware, and you want to rely on more of a computation and a computer intelligence. That's the trade. Please.
Did you ever consider using wheels instead of flat feet?
Well, it sort of felt the feet he had was rather compliant, so it would give you a natural motion of the way he wore it. So if I put wheels on the leg, that would be like a skating, I guess, So no, we didn't consider that. But please.
Is there one engineering discipline that's more important that you would emphasize to your students?
Very good question. Actually, I would say mechanical, electrical, computer science, biology, everything is important in this. And what I want to let you know, it's very important that you bring up among students should know that. Number one factor gets us anywhere really is not the knowledge, it's a passion. Once you have the passion, you create the knowledge. How long does it take to study these disciplines? Not much, just 4 years we teach all the tools, right? But using the tools to get to the target, that requires passion, not tools. Of course, it requires tools to do the right things, but tools can be obtained. Classes can be taken. Books can be read. The question is passion and intelligence, put them all together. So all these disciplines are equally important to me. I can't really pinpoint it. Obviously, we have computers, so we need a computer science. We have all the electrical circuits to do. We have all these mechanical structures. We need to look at interaction with the humans, so we need biology there. But I really can't pinpoint. Of course, I'm an engineer, but it's all in it. It's all in there. So I can't really pinpoint anything. Thank you. Please.
It sounds like you've been really instrumental in helping to create a culture where the emphasis is on taking things out of the laboratory and not making them overly complicated and putting them to practical use. And I wonder, is that something where you've had to sort of work hard to do that because of that tendency among scientists and engineers to want to make things, complicated and...
In order for you to give an honest answer, I got to have a glass of wine here. But scientists want to learn more and more and add to the body of knowledge for the good of people. And that's you can go far. But it is really easy to go far for getting where you are, especially these days. So it's no one's fault here. I'm not blaming anybody here. I'm just saying this is the way I am, and I want to work with people who are thinking about it. But we do need also people who are going to go by themselves far for a distance, just how far they go. So there are these two schools that are available here, but somehow I feel a sense of urgency here. We have a lot of young people, talented. You just saw Austin living. He's a sharp man, and at the age of 22, he's not able to walk. So being upright and mobile, standing, looking eye to eye, and going out to the movie without just thinking about it, how am I going to get to the movie with the wheelchair or something. There's a lot going on. I can't go into it with you. I'm sure you can figure this out. Getting technology out there to people somehow, I think it complements very basic principles of academic. Sometimes that I can't describe and I can't pinpoint it, but I
thank you for pushing in this direction.
I told you I'm very lucky and managed to be able to do that. It's not that I appreciate it, and it has been hard sometimes, but altogether it has been like a roller coaster. It's being in a position to actually do this stuff is, quite frankly, is the only thing that's empowering me to just walk around the street and feel I'm okay.
You were able to sell the Hulk idea to defense contractor. Are you finding prospects for commercial application for mobility disorders? Are there companies chomping at the bit to buy that technology and develop it?
That's what we found at Berkeley Bionics. It's a company that everybody has included here. So I'm not even working at Berkeley Bionics because I came back to work at the university. But in order to bring technology to people, the university can start but can't finish. We don't manufacturing. So many companies don't want to get into that because it's risky. So the way to do that is to start it up, and then it will take off on their own. And that's what we wanted to do. With the help of the university, we want to start an entity for this low-cost Ekso. I went anywhere. I went many places. I've been talking to a lot of good people who have funding if they can donate. Sometimes we're lucky, sometimes, most of the time, very unlucky because people don't have that much money these days to put in. It requires a substantial amount of funding to create an industry. My dream is to have the largest bionic industry in the US. It can be done within 5 years. We can do that right here in Berkeley within about probably $30 to $40 million required. So we can have not only facility for development, but also to manufacture. We can definitely do that, and we can bring right technology to right people, right here in Berkeley. That can be done. Again, you have the talents, you have engineering right here next door. Very, very, very dedicated people around the world, and that's what it changed my outlook of the world when you see passionate people from all over the world come here. A bunch of fellow students help another person along. That is a lesson to all of us who are a lot older. These guys are only 20s. Right? A lot of us are in 50s. Right? So definitely can be done. And I told before, I'm not trying to impress you with that, but to me, creating an entity that has the largest bionic feature, not only for medical application, but also for civilian, like FedEx, USPS, warehousing, constructions, all that stuff. Definitely good. I've been trying, but I have limited time. My urgency right now is on medical, and then hopefully if I can do that something within the next few years, maybe I will move. It inspires other people to move, like yourself. Just move in there. Because now, it's medical is done, maybe we can do civil. But we have some limited bandwidth here. There was another question. Yes, please.
Does your lab work directly with any central or peripheral nervous system interfacing, or do you work with other labs that
I didn't go through that, but we're doing some brain-machine interface right now. That means what you think sort of had to get coded on a machine language. On a very simple basis. Basically, I don't want to go through details, but we have really 5 functions that I want to go. Nothing very sophisticated. I want him to stand up. So stand up. Stand up. Walk. Go a little faster. Then go slower. Stop. And sit. This 5 functions is a game changer. Because then allows them to get on the exit, go outside, go to the restaurant, sit, or go to work, go to the computer chair to work and sit down and work and get up and go back at the work. So we're looking at a very simple, practical brain interface, machine-brain interface, but unfortunately I don't have any collaboration yet in Berkeley, and hopefully we'll go that. But that is a little bit far in the future, I would say, a few years. It's pretty advanced, as you know.
Well, isn't there also some prosthetics that they work with the peripheral nerves too as well, that people can learn how to, not exactly like thinking to walk, right. The impulse itself.
They're all in a research station, they're all in a research setting. But you're right, there are a lot of ENG-driven devices. But those signals are not really reliable as much. They're noisy, as you know. So it requires a lot of decoding to get the actual. The key is, it would be easy to do that in a healthy body. But we have a patient in there. And if I'm getting some peripheral signals, it better be really reliable, because I don't want to fall on the street. I mean, that's reality. Yeah, in the laboratory, we can do all kinds of things. We can have harness, safety, all kinds. People around you, he will never fall. And he can do a BMI or peripheral. Can he go out by himself 100%? That is the question I'm trying to get at.
Need a training period.
Yeah, and also it has to establish a level of confidence in me that he won't fall. Right? That's just, he can't get up. That's it. Please.
Where does your passion for this come from?
You're putting my spot here now. We all have it, I think. We all have it. Everybody has it. It just has to show up. I mean, we all have it. I don't think any different.
I was curious, like, if you were to take away the leg component of the Hulk devices, how does that limit the ability for the device to bear weight? And I guess kind of on a related note, for the civilian devices, are there ways to reinforce the leg components so that will enable greater mobility?
I'm sorry, I missed the last word.
So, for the civilian devices, I was curious about whether there are ways to actually enhance the leg component to enable greater weight bearing or greater mobility, so that they could actually do other functions like
very good.
Faster rate.
Very good question. I had a visit from NUMI. You guys know about New United Manufacturing Facility, right in Fremont, and I saw workers moving around objects,
I found that the lightest, the heaviest objects to pick up is 25 pounds, which is really not much. So after I looked at it for a long time, also in GM facility, it turns out what really hurts these guys, and they have these workers, risk of injuries, is not on their arms, it's on their back. So all I need to do, basically, all we needed to do is to have the same device, making sure the forces at L5, the small right at the very bottom, is shared with the machine. So that's a really different application. So basically, when the worker goes down to pick something, 25 pounds is not much of a one at all. In fact, a lot of those guys do too, but not here. That 25 pounds of the load plus front load becomes like 55, 70 pounds. So it becomes a posture problem, not a weight problem. So for a lot of people, especially in assembly areas, there's not much load. All they have to do, they go here in a trunk and a tighten screw. That's all they do. So it's not about the load, it's about the posture. So that posture is not helping for a long time to do this thing, right? So you need a device here in the back. So I'm not sure if I'm answering your question or not, but basically what Ekso does is it minimizes the force at L5 without any arms. Again, minimal design. I don't need any arms to make it Superman type machine. Please.
Do you accept volunteers?
Oh yeah, of course. We have volunteers. Of course I do. We have, in fact, the movie you saw, the 9 minutes. Did you see that? That one was a very young movie maker who wanted to be embedded in our laboratory, and I never turned down these, talented people that they come here to do the job, because this is what happens. You see, they're able to actually capture the essence of what we're doing in a few minutes, and I've been always impressed and surprised by a lot of people. It comes back to your question where the passion really comes, and I honestly believe everybody has it. We just have to sort of bring that up. It becomes our guiding light in everyday life. Since I've been doing this stuff, I'm a much nicer person to people. So, it really is there. So we just have to get I accept, of course, accept one.
Thank you, Professor Kazerooni.
Thank you. Actually able to manipulate, get a sense of how much you're picking up. Like if you're picking 200 pounds, you get a sensation of you're picking up 5 pounds. So you have that sense, which is a very good thing to have during manipulations. Later on, we moved on, and so again, going back to the less is more. We're trying to minimize and minimize, and I was all thinking about how to get this to people from the laboratory, which is always expensive and very complicated devices. But the real life requires something a lot simpler. So here you can see, this is again in the video, it's about 15 years old. You can see this robotic device. There is no really leg associated with that, and this person simply moves a big box of about 70 pounds, 80 pounds with 2 arms. Very simple. So that was a lot simpler because we don't need legs. And more importantly, we always believe that on a factory floors, if you are doing augmentation, if you're giving strength, there is really no reason to have legs. Everything can be hung from the ceiling. So why don't we just design an exoskeleton that comes down from the ceiling, and I can wear it and move around heavy objects, and just forget about the legs altogether. That would make the device simpler. So we did a lot of work, and this is a video of me on GM assembly, because I went actually to GM, and I saw a lot of these people. These are all my own photographs. I always wanted to know what they do and why do they get injured. They have back injuries all the time. And these guys do that once every 45 seconds. The car comes in and they pick up this, for example, this is both of those. Upper extremity is for moving objects and lower extremity is for walking. Very, very clear. But we have never really connected those together, mostly the way, because there is a technological barriers, and also there is no market needs. I'm the kind of person that I
I really believe in less and more. I believe in intelligence, but a smaller device that is accessible for larger, number of people. So we really never put this stuff together. And it seems to me that once you just make a whole device that you guys go in there and do everything, you just suddenly become Superman. And we haven't really done there because there is really a market need for it, so no one supports it anyway. It might look really good on TV and reporting, but there is really no application for our workers or patients here. And also we have some technological barriers to deal with that, which is not solved yet. Going back to the history, again, I apologize for the tone of this presentation. Most of our work is supported by Department of Defense, but it has application in all aspects of our life. And I'm hoping to show you that through these presentations here. So this is an application that Air Force were thinking about. It takes 5 men to load an aircraft, right? And in fact, actually, there is a 6. There is another one behind of this person that you can't see. In 1985, we came up to this concept of loading using this machine. Can we use this machine instead of forklifts? That has a factory application, it's manufacturing application. We really never finished it, but that was really showed that that's possible. We had a device that rather than just lifting, we also have a lot of people with mobility disorders that they don't even have a basic functions. And is there any way that we can robotic devices that give them some strength along? They basically have to sometimes zero. If they're stroke patients, it's one side of the strength. So this really shows the history before I get to black and white photographs. This is like a color photograph. There are some histories you can go back, and I have lots of interesting photographs from General Electric when they thought, okay, we're going to make mechanical systems you can wear and you can jump over the building and bust through the doors. It's very science fiction type things, which is really not real. And then until 1986, this movie Alien showed up that was the very first time that they actually showed an application for that. And it took about 20 years or more that we came up with this device, which is really minimal. It really comes back to less is more. That you can actually carry heavy objects with it without risking back injuries in your back. The question really we were forming in about 20 years ago, how do I, for example, in workers, make them stronger in terms of moving around heavy objects, have a better work environment and not to become injured in their back or their wrist or anything. So that was like our theme of the work. It wasn't about science fiction. It wasn't about jumping over the building. It wasn't about the stronger or something Superman at all. So that comes a little bit closer to what we were thinking about. And then in engineering, it's called exoskeleton because it's really outside of you. And the name it says it all. I don't have to explain that. And it really includes upper extremity and lower extremity. First failure of this. It's okay. It's okay. Is there any way that we can have robotic devices that gives you strength and endurance? And it has many applications. And a lot of people ask me that questions, how did I get into that stuff, is a long time ago when I was working on a lot of robotic devices, I realized robotic systems by themselves only can work on a very structured environment, like spray painting, assembly in cars, spot welding. You probably have seen a lot of videos of robots in other industry firms, and that's really good. But unstructured environment, like filling up the truck in a FedEx, right? Or working in a construction environment. These places you really can't replace a robot. You need a person. You need something very intelligent and adaptive to make decisions. And culturally, we can't replace people with robots. That's many places that's really not an acceptable thing. And we need human in the loop at all times. And so we're accepting that on dangerous tasks, we do, replace people with robots. That's like it's being done quite often. But we thought about coming up to a situation. Why don't we combine intelligence of a person with the strength of the machine? So you bring them together. You create a better quality of work for these people, and that means large class of workers. warehouse workers, distribution centers, auto assembly, construction guys. This is sort of a dream for us. It's not going to happen very quickly, but the trace, if we trace everything we have now, it is coming up to maturity at some point. And then my name is Homayoon Kazerooni. I'm a professor at the University of California, Berkeley, Mechanical Engineering Department. I've been here since 91. It's about 20 years, and I think I'm one of the luckiest guys actually to be able to the kind of work I did at Berkeley. I've been among a lot of good people, very talented people. I would say, without exaggeration, every single day of my life has been exciting about this stuff. It just, I can't take it anymore. It just, it really is that way. And so, what I want to tell you a little bit about the things we do with a lot of sharp students and engineers at Berkeley. That is also intertwined with my life now. 20 years. It was a job first. It was interesting, but now that I'm getting older, it's becoming a mission, becoming a lot more now. And we'll talk about it later on. But let's talk about engineering for a little bit. There's a concept called wearable systems. So robotic devices you actually wear, and it does two things. It gives you strength, and it gives you endurance. And these are really two different things that most of us are familiar with. When you go to gym, you actually do weightlifting, so that's really strength. And endurance is really no more than cardio, basically. Your oxygen consumption drops. You'll be able to actually go farther. You can